So, Alberto, are you ready?
Yes, I'm here.
Okay.
Hello.
So, my pleasure to introduce Alberto Marcone, professor in Udine, and he will tell us about Weihrauch reducibility and his usefulness to classify theorems. So, Alberto, when you wish.
Yes, thank you very much for the introduction. I still need to find a way of sharing my screen, which I don't see how to do this right now.
So there should be some share screen button at the bottom of the of your screen.
Oh, here it is. Okay, it was the
right, and then you can choose the.
Okay, here it is.
Okay.
Okay, I assume you are seeing my screen now.
Yeah.
So I wish to thank the organizers for inviting me to this talk. I also need to thank Professor Yokoyama because actually he already introduced my talk quite a bit during his talk. And I also thank all the people who are listening, especially those who woke up very early or are staying up late at night for listening to this talk. So I will, as already described by Keita, I will show a little bit, tell you something about the approach given by Weihrauch reducibility and the Weihrauch lattice in classifying mathematical theorems as before. So the approach is to start a little bit different from one usually taken by reverse mathematics. So we will view theorems as problems actually. And then I will need to tell you something about what we mean by computation with infinite objects. I will then be able to introduce actually Weihrauch reducibility. I'll do some comparison between Weihrauch reducibility and reverse mathematics, also working on some of the examples that already Keita mentioned. I will have a short section on parallelization, jump, and choice with two ends, I see, which are some tools that we use in this context of Weihrauch reducibility to calibrate results. And then I will finish off with a list of results which have been obtained, say, in the last 15 years at most. I mean, the idea of using Weihrauch reducibility to calibrate the strength of mathematical theories is younger than reverse mathematics. It has been going on for about 15 years now. So let's start by looking at theorems as problems. Many theorems are asserting that given some object X in some space, big X, if that object has some properties, which are here explained by satisfying this condition phi, then we will be able to find another object in some other space, Y, which is linked to X in some prescribed way. So there is a connection between X and Y. And we think that it is very natural to ask how difficult it is to find Y starting from X in a very general context. And we think of this as the theorem becomes a problem if we start looking at it from this viewpoint. We have X, which is an instance of our problem given by the theorem, and we want to solve the problem by finding a solution, which is some specific Y, which is linked in this way to X. And the Weihrauch reducibility in general terms is just a framework to give a mathematically precise answer to these kind of questions by comparing the difficulty of solving different problems which come from different mathematical theorems of this specific form. To convince you that actually many mathematical theorems are actually in this form, I have this page of examples. The first one is the one that already Keita discussed a little bit, the intermediate value theorem. Here, an instance of a problem is a continuous function from the unit interval to the real numbers. And the condition that such an instance should satisfy is to have different signs on 0 and 1. And then we are looking for an element of a unit interval which satisfies the condition that the value of f on this real number is 0. And so it's exactly of that form. In this case, our instance is the continuous function. Our solution is the real number, is the 0 for the continuous function. One of the zeros, because obviously there might be many solutions to a single problem. The function f might have many zeros. And also the other examples I have here, for example, the Bolzano-Weierstrass theorem. Here we are working in the space of a sequence of real numbers. The condition that a sequence should satisfy to be a meaningful instance for this problem is to be bounded. And the solution is a sequence of natural numbers, which are actually the indices for a converging subsequence from the original sequence. And Ramsey theorem for pairs, I'm fixing here the case of pairs in two colors, but I could do it for any number of colors and surely also for any size of the inputs. Well, the instance here is a coloring of a set of pairs of natural numbers with two colors. And the solution here is obviously a homogeneous set, what we call usually a homogeneous set. And also with Koenig's lemma, which was linked and discussed before as the main axiom of one of the big five of reverse mathematics. Here the instance is a binary tree. The condition to be a meaningful instance is to be infinite. And then we are looking for a path, an infinite path in the tree as the solution. So the function would be an element of Cantor space, a function from the natural numbers to 0, 1. And also Koenig's lemma, which is sort of the older brother of Koenig's lemma, the bigger brother, is now the input is a finitely branching tree on the natural numbers, say, and again, the condition is the same, infinity. And then also we are looking for an infinite path in that case, which will be now an element of Baire space rather than Cantor space. So these are all examples that just want to support the claim that many mathematical theorems, or even most mathematical theorems, can be viewed in this form. For some element, we are looking for another element. And these kind of problems can be viewed also and interpreted as partial multi-valued functions. Here, I'm not still specifying what are the spaces X and Y, but if I have a problem which comes from a statement like that, I view this as a multi-valued function f, which is defined on some subset of X, the meaningful instance is the X, that's the little x that satisfy phi. And for each such X, which is in the domain of f, the set of solutions, the mapping of the multi-valued function is to the set of the elements in Y, which are connected to X by the property psi. And obviously, we are using the domain only for selecting instances, selecting elements of big X, such that this set f of X will be non-empty, so that we actually are defining a multi-valued function because f of X is non-empty. And Weihrauch reducibility is defined precisely to compare partial multi-valued functions of this kind. But obviously, I've been still quite vague up to now. So I didn't specify which sort of spaces, big X and big Y, we are considering, and I will do in the next slides. And first, I did not specify which sort of reductions between multi-valued function we allow when we define this Weihrauch reducibility. And for the latter choice, as is done usually in Weihrauch reducibility, I concentrate on computable functions, but I point out now, and I will not go back to this anytime later, we could make different choices, for example, feasible functions, arithmetic functions, or continuous function. And we get, by applying the same ideas that I will describe you in the next slides, also other kind of reducibility, say arithmetic Weihrauch reducibility or effective Weihrauch reducibility, which are, or continuous Weihrauch reducibility, which are useful, interesting, and they have also been studied and looked at. But the main attention is actually on computable Weihrauch reducibility, which is Weihrauch reducibility when I do not specify anything more. So I need to tell you something about computability in this context where we are working with spaces which are more general than the usual space of natural numbers where reducibility, where computability is captured by the notion of Turing computability. So I need to tell you something about computing with infinite objects. So as I mentioned, classical Turing computability deals with functional relations of a set of natural numbers, and then we extend in a natural way to other countable sets by using the connections between a countable set and the natural numbers. And we want to extend computability to spaces which might be and very often are uncountable. And obviously, the first test we need to meet is what we do with computation with reals. And actually, several different approaches have been developed for this, and they lead to non-equivalent notion of computability. So we have to be careful about the one we choose. And we choose what is called type 2 theory of effectivity, which I think is very natural and very much connected to Turing computability. The idea here is that we are going to extend the notion of computability to a quite wide class of spaces, second countable T0 topological spaces, or more general, what we call represented spaces, which I will introduce in a little bit. And so computability over reals is eventually just a particular case in a theory of computability with mathematical objects, which perfectly fits our needs for studying functions, multivalued functions, which arise as problems coming from mathematical theorems, which deal with all sorts of spaces. And actually, this idea goes back in part already to Turing. It was developed already in the 1950s, so it's surely not new. And here the names are those of Gregorczyk and Lacombe. And then it had a new impulse, and it was brought forward by Klaus Weihrauch in this school in Hagen in Germany, starting from the mid-1980s, so about 35 years ago. So the idea here is that concrete computing machines, which actually try to do and do some computations, so also with some approximation, at least to real numbers or other mathematical objects, do not manipulate directly this kind of mathematical object, but they perform computation on sequences of digits, say of natural numbers, to be quite general, which describe in some sense the objects we are dealing with. And so most mathematical objects will actually require an infinite amount of information to be described in complete detail, let's say. And so we need to extend the classical theory of computation to infinite sequences of natural numbers. And an infinite object here so is described by giving better and better approximations, by increasing the precision with which we approximate the object. And also the output of a computation, if we are looking at a function, will also be produced by approximation given with increasing precision. So at the final stage, we don't have really the output completely given. We have just the output up to some error, which decreases as the computation goes on. And so we need to expect, and this is in stark contrast with the classical Turing computability, we expect that the computation never halts, because the computation needs to produce better and better approximation as we move forward following the computation. And the abstract model of computation is represented here. We have Turing machines with 3 tapes. We keep a distinction between input tape, a working tape, and an output tape. The input tape, we imagine that it's already initially completely filled with the input, which is a sequence of natural numbers, an element of Bayer space. This is a read-only tape because we don't want to mess with the input. The input is that one. It needs to be kept the same throughout the computation, but we can move with, well, this little triangle here as the idea of representing where my head is. It's looking now at number 85 in my picture. Then in the working tape, we can do whatever is needed, whatever the algorithm actually will tell us to do. So we have a head here which can move in both directions, left and right, and can write, erase, it's read and write this tape as the one in the usual Turing machines. And then we have an output tape, which is write only. So we are just writing on this. We are not doing computation. We are just writing the input. And we are moving only on the right side. So if we have already filled in the first 5 bits of our output, our head will be here. And at a given moment, will be instructed to print something at this stage, say it prints number 7. And then it will have to move 1 step to the left and go here to wait for the next output to be written. So in this output tape, we are not allowed to delete anything. And this actually is an important feature because since we are not correcting the output, the partial output we received, for example, this first 5 digit is reliable. If we were allowed in a future stage of the computation to delete some of these elements, we couldn't trust these 5 elements at all. But since we are in this write-only tape, we can trust that this will be the beginning of our output, and then new elements of the output will come out. So the idea is that in a computation, we supply an element of the input tape, as I described, and the machine will eventually write bit by bit an element of Bayer space on the output tape. So this is the abstract model of computation which we are dealing with, and which in some sense extends Turing computation, which can be viewed as we have just an input tape with just the first cell filled in, and we want on the output tape just the first cell to be written up. And so when we do the first cell, we can as well stop. I mean, there is no need for going forward in that case. We can also view Turing, this kind of Turing machines as ordinary oracle Turing machines. And the idea is that we put in the oracle actually what is our input, the infinite sequence of natural numbers, which is our input. And we can ask to the oracle to know about bits. So this is just like as the read-only input tape in my previous model. And we run a certain program, a certain algorithm on input n when we want to know what is the nth element in the output tape. So to really get the full output, we should run this machine on all possible inputs from 0 to all natural numbers and read what are our answers, obviously, if the computation succeeds. So this is equivalent, and this leads to this notion of computable partial function from Baire to Baire, which in some computability theory literature is also called Lackland functionals. And we should point out and keep in mind that these computable partial functions are always continuous, because they will give you more and more output based on a finite amount of input that it has scanned up to that point in the computation, up to the final stage of the computation. And so there is this continuity built into the computability. But obviously, we are not happy yet, because we are just computing function from Baire space to Baire space. And it's true that in some cases we will be interested in a multi-valued function from Baire space to Baire space, but in general, we want to consider much more general spaces, and so we are not happy with just this kind of solution. And so we need this notion of representing a space using Baire space as a sort of a base of our representation. A representation of a set, an arbitrary set, which, well, I often call a space, but it's nothing else than a set, is a surjective partial function from Baire space onto X. So every element of X needs to have what we call the name, which is an element of Baire space, and not all elements of Baire space need to be names for some elements of X. Some elements are just not names, and it's fine this way. And so a name for X is an element of Baire space which is mapped onto this specific element X, and this way we obtain a represented space. I underline that there might be multiple names for a single element of X. This representation need not be injective at all, and in many specific cases, it's natural to have non-injective representations. And in some sense, representations are analogous to the codings which we use in reverse mathematics and which are implicit in much of the things that Keita told us about reverse mathematics before. In reverse mathematics, we code various mathematical objects in subsystems of second-order arithmetic. For example, we code continuous functions or even Borel functions, which are not directly in the language of second-order arithmetic. And here the analogous is this representation idea that we represent elements of some space, say the space of continuous function of the unit interval, for example, into the real valued continuous functions of the unit interval. We represent them by elements of Baire space. And there are some obvious injective representation. These are representations that are not even real representation. For example, if we have a set of elements of Baire space, then the obvious representation is just the identity map, which is a partial function restricted to set X and associated to any element of X itself. It's already an element of Baire space, so it's its own name. And identifying subsets of natural numbers with the characteristic function, this also allows us to represent in a quite obvious way any subset of natural numbers. And then we can represent spaces of countable structures, such as graphs, groups, exactly by identifying them with specific subsets of the natural numbers. And also, let me point out, for example, in some spaces and also in some work I've done myself, we need to consider only sets of natural numbers, of sets of infinite natural numbers. And in this case, there is also another natural name, which is different from the characteristic function, but is the function that enumerates in strictly increasing order the set we have. So these are just some obvious representations which are so natural that they don't even get mentioned in many cases. More interesting representation, for example, we want to speak about real numbers. I mean, we said that this was a sort of a test for us. And so how do we represent the real numbers? Typically, we represent what we call the Cauchy representation. Well, first of all, let's fix a bijection between the natural numbers and the rationals. And the Cauchy representation of a real number is a sequence of rationals, which are represented through this alpha function, a sequence of rationals which are converging to x, but not only. We require the convergence to happen at a prescribed speed. Typically, we ask that the difference between one rational and the next one in the sequence is less than or equal to the minus the stage of a sequence at which we are. So this means that when we see a Cauchy representation of a real number, this is actually a Cauchy sequence converging to x, but not only Cauchy, it's actually, we know the rate of convergence of this sequence. So when we see the nth element in this representation, in this elements of base space, which represents the real x, this actually leads us immediately to a rational number, which is less than 2 to the minus n plus 1 away from x. So here really it's the idea that we have better and better approximation in this case of real x as we go along the representation of a real we are looking at. And once we have a Cauchy representation of real numbers, we can move to represent also in a Cauchy way the elements of a computable metric space. So what is a computable metric space? First, well, it's a metric space X with a metric D. And then we also fix an enumeration of a countable dense set D, which allows us also to be able to compute in an effective way the distance between two elements of D, starting from just the pair given by the indices of those two elements. And if we had done this when we define the Cauchy representation of the space X, exactly as before, when P is a name for an element little x in this space big X, well, if the sequence given, the sequence of elements of a dense set D converges to X and converges at the prescribed speed exactly as before. And again, as we progress in discovering the Cauchy representation of an element of big X, we find better and better information, better and better approximation about X itself. And actually, when X, as in many cases, is Bayer space or Cantor space or Cauchy space, we actually, the Cauchy representation is just the natural one of giving one element at a time. And in this case, is exactly the representation I described in my previous slide. So really, it's already covering those cases as specific cases, this idea of a Cauchy representation. But notice that in the Cauchy representation of an arbitrary computable metric space, or even just in the Cauchy representation of reals, I had here, names are not unique at all. There are many Cauchy sequences which are converging at a prescribed rate to the same real numbers, obviously. So here it's an important case where the representation is not injective at all. Now, another kind of representation we are using, and I will mention it also later, so I'm putting it up here, is representing a collection of closed sets. The collection of closed sets of a computable metric space. You can think, if you wish, just only of the reals, a closed subset of reals, or my picture here maybe suggests that we are looking at as a closed subset of a plane, of a Euclidean plane. So there are several ways of representing actually this space of closed set. What I am interested especially here is the negative representation. So the set I'm representing is actually this set which is here, this big set here, and I'm representing it by listing in my element of bare space open balls which are sort of special because I want to identify them just by natural numbers. So the center will be in the dense set and the radius will be rational. And so when I list a ball, the ball should be disjoint from the closed set I'm trying to represent. So I give negative information about the closed set. When I put this ball, I say, well, my closed set does not intersect this open set. Then I say this does not intersect this open set. Then I say this does not intersect this open set, and so on. I give the closed set is away from these open balls, and then I will continue moving on and describe new open balls here and maybe here. And my way of drawing picture is not very good, but eventually I will fill in all the complement of a closed set by these elements. And in this way, I'm representing the closed set. And this works for arbitrary computable metric spaces, but in some cases, it's also equivalent in a sense, computable equivalent in a sense that can be made precise by converting names in one representation to another one, to the familiar representation when we represent a closed subset of bare or Cantor space by a tree, and we say, well, the tree is representing the closed set which consists of the paths. We usually say the body of the tree, the paths that are going through that tree. And this is actually equivalent in this specific case, but obviously the negative representation is much wider application. It has wider application because it works also for spaces which are far different from bare or Cantor space. Okay, just checking the clock. Another notion which is important here is the notion of realizers. So say that we have a function connect between two represented spaces x or y. This function might be partial and might also be multivalued. What is a realizer for f? Well, a realizer for little f is a function big F, which is working at the level of names rather than at the names of functions. So it maps a name for some element in the domain of little f to a name for some element which is in y, which is the element in y, which is in f of little x. So this is the idea. It's quite natural. There is a sort of commutative diagram here. I say sort of because here on the bottom side, I don't have really a function, but rather a multi-valued function. So I need to be a little bit careful. But whenever I start with a p, which sends here to something meaningful in x, which can be mapped to something here, then I will maybe reach the same idea here. It's important to notice that different names for the same element in the domain of f might be mapped by the realizer big F to names of different elements of f of x, and this is perfectly fine because maybe the idea is that we are able in some cases to make a computation. Maybe big F is computable, but the computation depends on the input, depends on the specific name you fed to the computation. And so we want to allow for this, and this is fine for us. Now, we say that a function is computable, a multi-valued function, a partial multi-valued function is computable if it has a computable realizer. So we moved the notion of computability from just functions from bare space to bare space to function on represented spaces, and even to multi-valued function and even to partial functions. So this is surely it makes sense, and we achieved this idea of extending the notion of computability. By the way, we could give a definition of what it means for a multi-valued function of represented spaces to be continuous. Just in this last line, substitute continuous in place of computable, and you get just the same notion, or Borel, or whatever other notion you have that makes sense for single-valued function on bare space. Now we have set up the stage for actually defining Weihrauch reducibility. And historically, this was introduced by Weihrauch in the late 1980s. And the connection between the classical reducibilities, which are studied in classical computability theory, is probably mostly with many-one reducibility. But it has also some twists, so it's not really an extension of many-one reducibility. Now we call this Weihrauch reducibility, and Weihrauch and his school studied them already in the past century, in the 1990s. But really, the idea of using it as a tool for comparing the strength of multivalued functions coming from mathematical statements, this is a little bit later. It comes, well, between, let's say, 2008 or something like that. So here is the notion of Weihrauch reducibility. We have two multivalued functions, which might be also partial between represented spaces. So the first one goes from x to y, the second one from z to w. The idea is that we work at the level of names and of realizers. So we need to have two computable functions, the so-called forward functional h and the backward functional k, which allow us to make the transformation. And these need to be computable. And if here in place of computable, I put some other notion, I will obtain those other Weihrauch reductions I mentioned before. And the idea is that if I see the name for some element in the input of f, some little x which is in the domain of f, so the name is p, I feed this name to capital H, which works on bare space. This H will transform this name into a name for something which makes sense, which is a name for something which is an element in the domain of a function little g, to which I'm reducing f2. And then I will apply some realizer, which I don't have control of, some realizer of little g, and this realizer, big G, the purple one, will give me some name for some output in G, some output, some elements of G of that input. And then I use capital K, which has also access to the original input, little p, but has also access to this element gh of p, which has this name, which has been obtained. And k should work in any case to get a name for some member of my original problem, some solution to my original problem, which would be an element of f of x. And so in this case, if we are able to do this, we write that f is Weihrauch reducible to g, and I use this notation here. And so the idea here, again, and just to repeat it in a slightly different form, but totally equivalent, is that h is the first functional, the forward functional, is modifying a name for the input of f into a name for some y, which is in the domain of j. And then capital K, the backward functional, will, using also the name for your original input, will transform the name of an element of g of y into a name for an element of f of x, which is really what we cared about. So we are using a g to compute a solution to the problem, to the instance of a problem related to f we started with. And we obtain a reduction, which is in particular reflexive and transitive. It induces an equivalence relation, which is the Weihrauch equivalence relation. And obviously, we call this Weihrauch equivalence classes the Weihrauch degrees. And it turns out that the partial order of the set of Weihrauch degrees is a distributive bounded lattice. And there are lots of natural and useful algebraic operations. We call all of this the Weihrauch lattice. I won't go much into details about these operations which we can put. There is quite a bit of literature about this also in, let's say, the general setting of studying the Weihrauch lattice by itself, even without explicit connection to any specific theorem. But I'm putting the I want to compare a little bit shortly what's the difference between Weihrauch reducibility and reverse mathematics to compare these two approaches. So in a paper with Guido Gherardi, we started looking at using Weihrauch reducibility, which was already there, ready for us, let's say, to classify the complexity of theorems. And this program has been pushed out by many other people. Well, Vasco Bratka surely is a name, Guido Gherardi, which I already mentioned, Arno Paoli, many other people. And we found that in most cases, it's usually Weihrauch reducibility is compatible with the classification by providing by reverse mathematics. And this happens because in reverse mathematics, we are trying to prove a theorem, say, of this form, the form we are working with mostly of this kind here. And actually the proof is a description of the construction of some y starting from some x. And the axioms that we need in this construction will obviously give us information about the difficulty of finding y, which is really what we care about in the Weihrauch context, in the Weihrauch lattice context. But usually the Weihrauch lattice is more fine-grained than the reverse mathematics classification. And I'll give you soon some examples of how statements which are equivalent over RSA naught may give rise to multi-valued functions which have different Weihrauch degrees. And this occurs because our notion of Weihrauch reducibility had two constraints which were both pretty strong. One was uniformity, because we were using, going back to here, the same h and the same k for no matter what the inputs were. And these need to be computable, so there is some uniformity requirement. And the other one is that we are allowed to use the harder problem, the G, just a single time. We can use it only once. And this is what happens here in this picture. We are not allowed, after getting the output of G, to go back maybe to G by doing something like that. Weihrauch reducibility does not allow to. Obviously, we can generalize and get something like that. So this is not allowed. So there are these two constraints, and this leads immediately to some finer, more fine-grained classification than the one provided by reverse mathematics. Let's start with an example immediately, which is our old friend from today, the intermediate value theorem, which has been mentioned already many times. So actually, in the reverse mathematics context, as Kate already mentioned, this is provable in RCA naught, and the proof is sort of a standard proof you probably give in a calculus class. Given the continuous function from the unit interval into the reals with different signs of 0 and 1, first you ask if there is a rational solution to the problem. There is a rational number which takes value 0. In this case, we are obviously done. Elsewhere, we basically run the bisection method. We know that at any rational, we won't find a 0, and this allows us to check whether the numbers we compute for the bisection point is positive or negative. And when we realize it, we move either to the left interval or to the right interval, depending on the sign of that one. And eventually we are converging at a prescribed speed also. So we get a Cauchy representation for the real that we are looking for, which is a solution to our problem. This proof is highly non-uniform because of that initial distinction. There is a rational solution, there are no rational solutions. And reverse mathematics cannot catch this up, or maybe it can catch it up as in the way that Keita described by looking at sort of parallel versions, but Weihrauch reducibility catches it up immediately, because if we look at the intermediate value theorem function, which is described here, but it's the obvious one, already in 2000, Weihrauch realized that this intermediate value theorem has no continuous realizer, so it has no computable realizer, because any continuous function from Baire to Baire will be continuous, and in particular, so it's not computable at all. So while we expect theorems proved in RCA naught to be able to correspond to computable multi-value functions, in this case, this does not happen. And here is because there is this lack of uniformity in the proof in RCA naught of the intermediate value theorem. And it tells us that it's not our fault. It's not that we are missing a nice uniform proof, a nice computable uniform proof. There is no nice computable uniform proof of intermediate value theorem. And so this is where lack of uniformity really matters, and Weihrauch reducibility catches it immediately, without resorting to parallel versions where we repeat many instances and countably many instances of intermediate value theorem. Here we're looking just at a single instance, it's there. Another example where Weihrauch reducibility is able to catch, to detect some differences in detecting iterations. So we are again going back to the infinite Ramsey theorem for n to plus n k colors. And we use the same notation for the multi-valued function, which is naturally arises from it. And we know in reverse mathematics, the strength for RT and K depends only on n. And actually, if n is larger than or equal to 3, it doesn't even depend on n. But let's fix n, which might be 1, 2, or 3, or more than 3, doesn't matter really. Well, and just look at changing the number of colors. If you have more colors, k colors, which is more than j, then the proof in RCA not, which is the obvious proof, will go on by merging some colors. Say that k is 2, k is 3, I'm sorry, and j is 2. How do we prove Ramsey theorem for three colors from Ramsey theorem for 2 colors? The colors are red, blue, and yellow. We merge blue and yellow, say, into green. And then we apply the theorem to this, which has just 2 colors, red and green, and we obtain a homogeneous set. If it's red, we are already done. But if it's green, we reconstruct the original blue and yellow colors and apply Ramsey theorem for 2 colors again. And so we use Ramsey theorem for 2 colors twice to get Ramsey theorem for 3 colors. And actually, we can do the same also for 4 colors. And in reverse mathematics, this is allowed because in a proof, we can use our hypothesis, the theorem, as many times as we wish. But several people, more or less at the same time, in different papers, Hirschfeld, Jokush, Patey, and Bratkaira-Kotoniana, showed that actually, from the Weihrauch computability standpoint, we can catch the difference. If k is larger than j, then, and n is always the same, then RT and J is properly stronger than RT and K, and the other way around. RT and K is properly stronger than RT and J. The reverse inequality is obvious. And so we are able to detect the need for iteration, and there is no other way of proving Ramsey theorem for 2 colors, for 3 colors from Ramsey theorem for 2 colors, other than iterate the proof. Use the proof twice. There are some exceptions where the reverse mathematics approach seems to detect some differences which are missed by Weihrauch reducibility. We already pointed this out in the paper, in the 2009 paper with Guido Gherardi, when we wrote, and I think it's still the best way I have to express it, so I'm still repeating it. The computable analyst, which is somebody working in the area of Weihrauch reducibility, is allowed to conduct an unbounded search for an object that is guaranteed to exist by non-constructive mathematical knowledge, whereas the reverse mathematician has the burden of an existence proof with limited means. And let me show you an example of this, which is concerned with the Heine-Borel subcompactness of a unit interval. So here I mean the statement of every countable open cover as a finite subcover. This is equivalent to WKL naught according to the reverse mathematics approach. It was already mentioned as a meaningful example by Keda. And but Weihrauch showed that one of the possible multi-valued functions arising from the statement is actually computable, because given an open cover, we can just start searching for a finite subcover. The truth of the Heine-Borel theorem will guarantee that our search sooner or later will succeed, and we can check computably whether any finite subcover is any finite collection of open sets would actually cover the whole interval. So from the reverse mathematics viewpoint, this algorithm can be defined also in RCA not, but actually the reverse mathematician needs to prove that the algorithm will terminate. It's a terminating algorithm, and this will require WKL not. So here reverse mathematics seem to get some differences which are lost in Weihrauch reducibility, where we think that the Heine-Borel compactness theorem is somehow computable. But the point is already mentioned here is that this is just one of the possible, here it is, one of the possible multi-valued functions. We can look at the Heine-Borel compactness as the contrapositive, given a collection of open sets which is not a cover, with such that no finite subcollection is a cover. We will need to find a point which witnesses that the original collection of open sets is not a cover. And if we do this, then we get something which is at the level of WKL naught. So here is also another, I want to highlight another aspect, that the same theorem, in this case the Heine-Borel subcompactness theorem, can lead to different multi-valued functions, and these usually are not equivalent, are not Weihrauch equivalent. So it's more fine-grained also in this way, that a single theorem leads to different formulations and different multi-valued functions. And this occurs in many other theorems, actually. So let's compare a little bit more Weihrauch reducibility and reverse mathematics by looking at functions which correspond to the systems above RCA naught, which were mentioned as the major systems of reverse mathematics. So here I have a function which corresponds to WKL naught, which I call just WKL. So I drop the 0 in the subscript, and it's the obvious one. Given an infinite binary tree, we'll map it to the set of its infinite paths. At the level of RCA naught, we have this natural function lim, which computes the limit of a converging sequence, say in Bayer space. There is not much difference between the spaces we are looking at. And we can also iterate it. I mean, I can use lim, get an output, use that output in a computable way to produce a new input for lim, and then compute the limit of this other sequence. And in this case, I will use the lim twice, and I will get to lim with a 2 on the top in place of that k. And in RCA naught, we are allowed to use some principle, which such as lim many times, and so we are allowed to move up to any iterate of lim. ATR is the function that just mimics the usual definition of ATR naught, which I think it was not given by Gata, but it's the usual one. And given a well-ordered X, you produce a jump hierarchy along X. And then Pi1CA is a function that mimics Pi1 comprehension, which, as Gata said, means that we are able to recognize which trees are well-founded. So you give me a list of trees, a computable sequence of trees, and I will tell you which one of the trees is well-founded and which one is ill-founded. So this is a function that naturally corresponds to Pi1 comprehension. And we will get back to statements or other theorems which are equivalent to these functions later. I need to do a little bit of detour to mention these constructions. One operation is parallelization, is one of those operations I mentioned. The idea is I have just a single multivalued function, but I parallelize it by giving countably many instances of a problem, and I want countably many answers to each of those problems. For each problem, we want an answer. So this is parallelization. We say that a function is parallelizable if it is Weihrauch equivalent to its own parallelization. And all the functions I mentioned in the previous slide are actually parallelizable, are very stable, robust. But on the other hand, the infinite value theorem or all the functions associated to Ramsey theorems for n-tuples, these are not parallelizable. So parallelizability is not always occurs. Another operation we make in the Weihrauch lattice, this is really not in the lattice, but it's the operation of jumping. We can use lim, which I described before, to define some sort of jump. It's not really fully satisfactory jump, but it's useful at least at the lower levels of a Weihrauch lattice. The idea is that the jump of a multivalued function f is just a function f, but the input is not given directly by a name of the input, but by an approximation to the name of the input. The input is given as a limit. So this makes obviously the problem harder. For example, the jump of WKL means that we are not really given the tree where we need to find an infinite path, but we are given some approximation of the tree which is still moving, and we don't know at which speed it's moving. So at any stage, the tree might still change completely its shape, let's say, and still we need to find a path through the tree. So this means that the problem is harder. F is always Weihrauch reducible to F prime. And in many cases, especially at the lower levels of Weihrauch lattice, we have the strict inequality we would expect from a full-fledged jump. But at upper levels of a Weihrauch lattice, there are also many examples where the jump really doesn't jump. I mean, it's a jump that stays in place. And so it's really not a fully satisfactory jump, but it's useful. And I will use it to describe some Weihrauch degrees later. So that's the reason for introducing them. Also, I want to introduce some milestones in the Weihrauch lattice, which are the choice function. If we have a computable metric space, I introduce the space of its closed subset, which is a representative space with a negative information. Those open balls I was deleting from the space to work and remain with only the closed set. And the choice function is a multivalued function that takes an input, a non-empty closed subset of X, and just maps it to the set of all its elements. So it just tries to pick one of its elements from a non-empty closed set. Notice that this doesn't really come from a mathematical theorem. The mathematical theorem will be a non-empty closed set as an element, which I cannot sell as a theorem to anybody. But as a multi-valued function, it's interesting, it's important, it's useful. So let's use this choice function as milestones for us. And I should point out that even if a space has just 2 points, already this choice function is non-computable. For example, if I apply the choice function on Cantor space, then this turns out to be equivalent, Weihrauch equivalent to the principle I called the function I called WKL before. So I already see some importance here. Also, it's important in some cases the restriction to these two singletons. You give me a singleton, but you give me a singleton not by giving me the element which is the only element of a singleton, but I deleting all the elements which are not in the singleton. And this way I obtain the unique choice function, which you see, and this is also useful. And if I restrict this to the space with 2 elements, in this case, this is computable because I'm sure that one of the 2 elements will be sooner or later deleted. And so I wait until you that are giving me the input, you delete one of the elements, and I'm sure it will be the other one. So UC2 is computable. In general, UCX is Weihrauch reducible to CX. In some cases, it's equivalent, for example, for the natural numbers. In some cases, Bayer space or Cantor space, these are actually 2 different Weihrauch degrees. I should also mention here that in some cases, the choice functions are just plain incomparable. And this is also to mention something that maybe was not apparent from what I said up to now, but there is a lot of incomparability in the Weihrauch lattice. There are lots of multi-valued functions which are incomparable. There are big anti-chains in the Weihrauch lattice. And an example of a small anti-chain from what I'm saying here is that the choice of the natural numbers and the choice on Cantor space are incomparable. On the other hand, if you look at unique choice on the real numbers is actually equivalent to unique choice on the natural numbers. So these are just some facts about choice. And then I want to come to the last part of my talk, which is just giving you a sample of results that have been obtained in the last 15 years, basically, where some of those we actually date back, especially about computable results, even more than 20 years. So in my first slide, I have a list of some multi-valued functions which are arising from theorems and which are computable. So I already mentioned the Heine-Borel theorem, that at least version of the Heine-Borel theorem, which is known to be computable, but also some of the theorems provable in RCA0, which were mentioned already by Keita, turn out to give rise to these multi-valued functions which are equivalent. For example, here, let's just mention the example of a Bayer category theorem. What I'm given is a list of closed set with empty interior, and a list of nowhere dense closed set, a countable list of this, and I need to find a point which is not in any of those sets. So to show that the whole space is not a countable union of nowhere dense sets. And this function is actually provable, it's actually computable, and I couldn't even find a reference, so I think it's folklore and it's very often mentioned. Then there are theorems which are equivalent to choice on the natural numbers, and this is a level where really there is nothing corresponding to this in reverse mathematics. And for example, here I have the Banach inverse mapping theorem, the open mapping theorem, the closed graph theorem. Many of these theorems were found actually in this paper by Bratka and Gerard in 2011. Also, the Bayer category theorem viewed the other way. You give me a countable collection of closed sets which cover the whole space, and I need to tell you which one has non-empty interior, because at least one need to have a non-empty interior. And so this happen at this level. Functions occurring at this level have always outputs which are computable in the input, but not in a uniform way. So here is uniformity that matters, and is pointed out by this C of the natural numbers function. And they also introduce this terminology that they are computable with finitely many mind changes. It means that on that output tape, you are allowed to delete sometimes, only finitely many times. From some point on, you will start writing only, basically. And this function can be computed this way by extending the machine, the power of a machine in that way. Then there are theorems which are equivalent of choice on Cantor space. And these are the ones that typically correspond to WKL not in the reverse mathematics setting. There are many results like that. Again, there is this contrapositive of the Heine-Borel covering theorem. There are more results like that. And these functions have always outputs which are low in the input, but not always computable in the input, because otherwise it will fall in probably in one of the previous categories. And so they are not computably, even if we allow non-uniform computation. These functions are all parallelizable and are equivalent to its iteration. So if I iterate Koenig's lemma many times, this is an observation we made with Guido in our first paper, we still keep it being at the same level in the Weihrauch degree. I see that time is a little bit running out, even though maybe I started a little bit late. Then there are functions which are equivalent to lim, and this is a short list of a monotone convergence theorem. These are typically theorems which are equivalent to SA naught, but not all theorems that are equivalent to SA naught are at this level. Here the outputs are always computable and actually uniformly computable in the jump of the input. We can think of this as limit computable. I don't want to go into details. These are parallelizable, but as lim, they are not equivalent to their iteration. Moving up, we find that some functions are equivalent to jumps of something. For example, we proved with Guido Gherardi and Vasco Bratka in 2012 in a paper which sort of had, I think, quite an influx, at least looking at from citations to the development of the subject, that the Bolzano-Weierstrass theorem for bounded sequence of reals is equivalent to the jump of Koenig's lemma. And also for other theorems, this has been also proved. Also, we can classify, well, Ramsey theorem for pairs, not really Ramsey theorem for pairs, but it's parallelization, which is a little bit stronger, by using the iterator of Koenig's lemma. This is a result of Bratka and Rakotoyaina. In the way that it's shown there, and so when you move up using more tuples of larger length, you move up also in the hierarchy, in the Weihrauch hierarchy. And then I wish to mention this recent result. I put 2022 because I think it's not yet assigned to an issue of the paper, by Marta Fiore-Carones, Paul Schaefer, and Giovanni Solda. They looked at a theorem arising from a theorem of rival sense about graphs. They look at the multi-valued function and show that it's actually equivalent to the double jump of WKL. So to a function which is even above. And there is no reverse mathematics version for this kind of results. The ones which are mentioned in this slide are all equivalent to SA naught, actually. But here we get a much finer solution to this problem. And then I push forward in the last few years, so I'm talking about mainly my results, mainly about results in which I was involved in the last two slides, in the idea of pushing the Weihrauch lattice forward, looking at the higher levels of the Weihrauch lattice, which I mean start from theorems which are equivalent or anyways are in the neighborhood of ATR naught and pi/1 comprehension. And so, for example, we found that some theorems of this kind lead to multi-valued functions which are equivalent to unique choice on bare space. Here there is also work with Manlio Valenti, for example, and the work with Takayuki, Kihara, and Arno Pauli. And then there are some functions which are equivalent to choice on bare space, which is properly stronger. Again, we did some work with some of my colleagues and Manlio when he was a student of mine. And then we also moved to theorems which are equivalent to pi/1 comprehension. Hurst was the first one to especially mention a theorem like that. And we found at least another example with Vittorio Cipriani, which is a current student of mine, and Malio. And so we have examples like that. And we also found many other we studied many other multivalued functions in this neighborhood, which are not exactly equivalent to any of the function I put here. So I have the last slide, which is the zoo of Weihrauch reducibility. Not all multivalued functions which come from mathematical theorems are equivalent to the milestones I described. There are plenty of functions in the Weihrauch which live in Weihrauch degrees which are maybe a little bit off a beaten path. And here is a list starting from multivalued functions coming from Nash equilibrium's theorem, which is quite low in the Weihrauch lattice, and moving up to theorems like the last ones in my more recent work, which are actually more in the neighborhood of the choice or unique choice on bare function or even pi over 1 comprehension. They are pretty close to that. And we have many examples of this. I don't even mention all of them here. But I think this gives you an idea that there are lots of relations, and we get a very fine-grained picture of a comparison between different theorems and different multivalued functions we are allowed. I think this was my last slide before my thank you for your attention, and a happy World Logic Day.
Yeah, so thank you, Alberto, for your interesting talk. Unfortunately, I think there's no time for questions, so maybe we should just move on to next speaker.
Okay, it's my pleasure to invite our last speaker, Professor Iskander Kalimullin from Kazan Federal University. So he talks about computable structures and isomorphism.
Okay.
Iskander.
Okay, thank you.
I don't know how to
Okay.
stop my screen right now. Let's see if I have just tiny button. Can you do it for me?
Same button, maybe in the below.
Yeah, it became a very small. Okay.
Oh, yes.
Okay, I think I did it.
Okay.
Or you did it for me. I don't know.
Okay. Now I will try to share. Do you see?
Yes.
Oh, okay. Okay. Thank you, the organizers, for inviting me for a possibility to have a talk on this nice day. I also congratulate everybody with the Logic Day, and okay, my talk is first I will speak about some basic definition, and then we'll go on the result. So the first notion, I guess it's familiar. It's we say that the structure is computable if the domain is computable and all relations and operations are computable. A computable presentation, it's just a computable isomorphic copy of A. Two computable structures are computably isomorphic if there is a computable isomorphism from A onto B. It's quite standard definition, and so the notion which I will study during my talk is computable categoricity. We say that a structure is computable categorical if a structure A is computably isomorphic to each of its computable presentations. So we know that there are sufficiently many natural examples of computable categoricity in the among standard computable structures. So we can take even the set of natural numbers with addition by 1. So because we can generate from from 0 any possible natural number, we can reconstruct the isomorphism computably. The same is holds for the field of rational numbers because it's also finely generated structures. In general, any finely generated structure is computably categorical by just by easy arguments. Another example of computable categoricity, it's the dense orders. So it says if we have two copies of the dense linear orderings without endpoints, then we can easily build some computable isomorphism between these linear orderings. So the ordering of the rationals also is computably categorical. But there are some natural examples of the structures which are not computably categorical. I guess its most easy example is the ordering of the natural numbers. But we can note that if we have the oracle 0 prime, then we can build such isomorphism. So it's exactly for this I use this definition, which is just a partial relativization of the notion of computable categoricity. No, first we say that a countable structure A and B are X-computably isomorphic if there is an X-computable isomorphism from A onto B. So it is just a relativization. And this is a partial relativization. In fact, we are still considering only computable presentation of the computable structure. And we say that A is X-computably categorical if A is X-computably isomorphic to each of its computable presentation. So we relativize the oracle for computing isomorphisms, but do not relativize the notion of computability here of computable structure. We still consider only computable structure. So and then it's easy to check that if you know the oracle 0 prime, then we can build some isomorphism between any two computable presentation of omega, or the natural numbers. And moreover, we will note that that 0 prime is the least such degree which compute all these isomorphisms. But it's not only one possible relativization of the notion of categoricity, of computable categoricity, which I should mention during the talk. Also, it's very important the notion of categoricity on a cone. We say that a countable, not necessarily computable structure A is computably categorical on a cone if there is a if there is some big degree, some high degree C, relative to which A is you can provide an isomorphism between A and every copy B using as oracle this cone-based C and the atomic diagram of this copy B. So so we need some big data C which allow to build an isomorphism from A onto every copy B, and we need only know only the atomic diagram of this. And in general, we can use also the atomic diagram of the A, but usually C just can be compute some copy of it. So it is, so this definition is correct. So it is it's one definition. It's one related notion is it's called relative computable categories. So the first notion is a very general notion. It's even can be can hold on some non-computable structures. This notion is quite strong. It is more strong than the usual computable categorical structure. We require that the cone base C is computable, and the structure itself must be computable. So that means that A is relative computable categorical if A is computable and it is computably isomorphic to every possible copy using this copy as oracle. So if the copy is computable, then we will have computable isomorphism. If B is any other non-computable, then anyway we can use the atomic diagram of B and calculate the isomorphism. This is important notions because it presents a nice connection between computable model theory and the pure model theory. So it is a famous result of Goncharov, which says that A is computably categorical on a cone if and only if, in fact, relative to some tuple, the structure is so-called exertionally atomic. That is, every automorphism orbit of any tuple in this finite enrichment is exertionally definable. Is definable by an exertional formula. And for relative computable categoricity, it's the same. The similar criteria holds, but we only require that we can find the families. We can find the defining existential formulas by a computable way. So we can enumerate the families of defining formulas which define every possible automorphism orbit of any tuple. So it is just a uniform effective version of this of the categoricity on a cone. So the first is we can note that this notion is just pure model theoretic notion. Here it is just and so, but the second, of course, it is depends on the complexity of the Scott family, of the defining family. And it is easy to see that these examples of computable categoricity, in fact, are very uniform. They are relative computable categorical. These examples of relative computable categorical structures. And in fact, it needs some more diagonalization, to build a computable categorical structure, which is not a relative computable categorical. But let us return to the first notion. So about the X-computable categorical, it is different from a categoricity on a cone. So we see here that 0 prime is the least degree such that some structure is X-computably categorical. This leads to the notion of degree of categoricity. I guess this notion is inspired by Goncharov, as I know, and it is quite a useful notion, a natural notion. And the first study of this systematic study of this notion was in our work, joint work with Russell Miller, Екатерина Фокина, where we proved two following theorems. First, every C degree, not only 0 prime as we saw just on the previous slides, but any possible C degree can be a degree of categoricity of a rigid structure. So yeah, I didn't pronounce it, the notion. Turing degree is the degree of categoricity of A if X is the least degree such that A is X computably categorical. It's quite natural from one point of view, but it's quite complicated from another part, but I will speak about later. So each C degree is a degree of categoricity. So each degree can be the least degree in which some structure is X computably categorical. And surprisingly, every 2C, so it is degree of the difference of C sets, is also a degree of categoricity of a computable structure. But we only need lose a rigidness. So it is not necessarily rigid structure, but it's some structure, computable structure. It's a degree. So this work caused a lot of another work which precedes these investigations, these results. So in particular, it was proved that we can relativize this theorem about any interval between 0 to alpha and 0 to alpha plus 1. For every successor ordinal alpha, even infinite. For finite, it was proved by in the original paper. But for infinite, it's more less obvious. It is Chima, John Franklin, and Richard Shaw. And this theorem does not hold for any degrees. So there is some degree X below 0 double, which is not a degree of categoricity of any structure. And the recent result by Barbara Chima and Kengmeng Enge, they proved that it's not even 2C degrees. Any delta 0 2 degree, any degree below 0 prime is a degree of categoricity of some computable structure. But the comparison here, that in comparison with our original construction, this theorem is is proved much harder. So it is there is a very big difference between this construction and this. And I will speak about why it is different. But also some later works showed that there are structures which have no any degree of categoricity. So we can introduce in general the notion of categoricity spectrum of the structure. It is the set of all Turing degrees such that A is X computably categorical. And the first nice result shows that there is an algebraic field such that categoricity spectrum of the structure coincides with the degrees of completion of Peano arithmetic. It's the PA degrees. And it's interesting that it is only one known natural example. It's only one case when we can say we can describe the categoristic spectra naturally as here. So it is some good some well-known class of degrees. And the question is, are there other natural categoristic spectra? For example, it is known, it is a result of the Doni, Iguza, and Melnikov, that for some A, so what it means, it's quite a nice result, which says that in other terms. So this structure A has the property that between any two computable copies of this structure, we can build an arithmetical isomorphism. But any finite level of arithmetical hierarchy is not enough to cover all needed isomorphisms. So for each level n, we can build two computable copies of this structure, such that no delta 0 n isomorphism between these copies. But every time we can build and some arithmetical isomorphism. So in the terms of categoristic spectrum, that means that the intersection of upper cones of 0 to n of finite jumps of 0 is subset of the categoristic spectrum, but 0 to n is not does not in the categoristic spectrum. And in fact, it's natural to ask, maybe this is the example of also some other natural categoristic spectrum. So can we provide maybe some making some improvement to this, because maybe without some modification of the original construction, can we build? Can we have so that categoristic spectrum of A is such intersection of upper cones? In general, intersection of upper cones is possible. I will show later that it's possible in general, not to 0 to n, for some collection of sequence of degrees. So do you remember that there are some crucial difference between rigid case and non-rigid case? For rigid case, we had C degree, only C degrees. Here we had 2 C degree, and for the result of Chima and Gare, we also they have some non-rigidness. And if we will study just rigid structures, then we first we can prove that there is a property 2C degree, which is not a degree of categoricity of rigid structure. So in fact, we cannot improve the first result, which is 2010, making rigid structure for DC degree. So there is a properly DC degree, which is not a degree of categoricity of rigid. This is the result of Bazhenev and Yamaleev, Nikolai Bazhenev and Mars Yamaleev. And another result is from 2018. It's Ekатерина Fokina, Andrei Frolov, and me. So there is a computable rigid structure without degree of categoricity. So it is so here it was example of the structure without degree of categoricity, which is generally is not rigid, but here is an example of the rigid structure without a degree of categoricity. And when the structure is rigid, there is only countably many pairs of computable. There is a countably many computable presentation of the structures. Its situation much simpler in general, and any computable copy presents on gives only one possible isomorphism between the original structure and this copy. And so, in fact, categoricity spectrum is just always some intersection of upper cones or this isomorphism between different copies of the structures. But it's possible to make that this sequence of the isomorphisms A0, A1, and it's unbounded. So we can select an increasing number, increasing sequence of degrees A0, A1, and that's a categoricity spectrum is the intersection of upper cones. So in general, my previous questions has some sense, and possibly it would be interesting to have a natural spectrum like that, improving the result of Downey, Ikuza, and Nelly. This is so in general, the rigid structures are more nice. So you can prove many or disprove some many results. So there is a, as I said, there is a properly DC degree, which is not a degree of categoricity of rigid structures, and this degree can be found between any two arbitrary C degrees. So it is such degrees is placed densely in the C degrees. It's the result of Nikolai Bazhenov, me, and Marcy Maleev. And now, returning to the notion of the cone, one can define the notion of degrees of categoricity on a cone. I will not define the precise definition of this notion, but it's interesting that the point of view of a cone, so it is when we are make some abstraction under computability content, in some sense, then every countable structure has the degree of categoricity. It's some alpha jump of some of C, where C is the base of this cone. So in fact, this result follows by some forcing methods from the existence of the Scott family at the level alpha of this structure A. So this result of Barbara China and Matthew Harrison Trainer. So it is so on the point of view of the cone. So only jumps can be the degree of categoricity. But I will. But now from this cone, I will just restrict only on not on I will go from arbitrary Scott sentences, which can be sigma alpha sentences, to the original E-atomic case. So it is so I recall that we say that A E-atomic is the automorphism orbit of every tuple A is sigma definable. So A has a Scott family of existential formulas. So I recall that this is almost the same as to say that A is relatively. So it's the same as to say that A is computably categorical on a cone. but on a cone does not mean that it's computable. So it is, in fact, it's natural to study what are the degrees of computable categorization or this simple case when A is existentially atomic. It is not difficult to note that if you consider only existentially atomic structures, then we can select a zero double jump Scott existential family, E family. In fact, because if you know that every automorphism orbit is existentially definable, in fact, the orbit, each orbit in a computable structure becomes a pi2 set in the structure, and so it's a pi2 sentence to say that two particular elements or tuples are automorphic using some pi2 sentence. Because it's just to say that these two tuples have the same existential theory. And for the situation of rigid structures, the situation is much simpler again. Every rigid computable atomic structure has a zero double or a zero prime C Scott effect. And that means that if this structure, so this means that every atomic structure, computable atomic structure, at least zero double computably categorical. And the rigid structures are zero prime computably categorical. And in the in the examples of the structures which has CE or DCE degrees of categoricity from the original paper by me, Xavier Fokin and Russell Miller, are in fact E-atomic. And in fact, they are categorical relative to that degree, exactly because there is a Scott family, E family, which can be enumerated in this degree. So this is main difference between. I will return to the. This is the main difference between our result, original result, and the result of Chima and Enge. Here we have we cannot separate any existential Scott family, E family. Here it is just it follows by a natural way that there are some nice E family. In fact, these structures are E-atomic. So, but in general, it is for this also it's not difficult proposition, which say that we for E-atomic structures we in fact the upper bound zero double in general it's optimal bound. So every sigma 02 degree above zero prime, in fact, is the degree of categoricity of some E-atomic structure, which has an XC Scott E family. So it is, again, we can enumerate this family, and using this family, we can build all necessary isomorphisms in the degree X. And again, the situation with rigid structures is much simple and old results from 2019. It can just reformulate it in the terms of E-atomic structures. So in fact, if we restrict, we will study only such cases when X is the degree of categoricity and the categoricity provided by some XC is called E family. So we restrict by E atomic structures in the very strong sense, then we can get only CE degrees of categoricity. So and the natural question arises: what is the situation if we will consider a general case, not rigid, arbitrary structure? So it's we know that there are some degrees which has this property. Any 2C degree has this property. It's a degree of categoricity of some E atomic structure with corresponding Scott E family. And CA above 0 prime degrees also are. How we can extend this? And my intuition says that at least for the degrees below 0 prime, we must have only 2 CE degrees. But I do not know. Maybe it is not true. But it's likely that it should be true, because this was so you see it was open for at least 5 or 7 years, and this result is which solved that question, which about the possible degrees of categoricity below 0 prime. It was solved by Chima and Enger probably in 2017 or about that. But it was the proof was complicated. They and the authors wrote this proof long time. So I do not believe that we can somehow we can extend this result by providing some natural way. So at least the categoricity. So why some structure is categorical in that degree? It's much simpler just to present some family of formulas, defining formulas, than to build isomorphisms between every possible computable presentation copy of this structure. So I think that only 2 CE degrees below 0 prime are only the degrees which are degrees of categoricity in that strong sense. The next slide shows another complexity which happens with the degree of categoricity. I recall that the structure is so the degree is the degree of categoricity if X is the least degree such that X is computably categorical. In fact, it is also why it is the least. In fact, usually how it is provided that some degree X is the least. In fact, it's the most simple way to provide that. It's just to present 2 specific copies of the structures, such that every isomorphism between these 2 copies computes this degree X. This properties was called a strong degree of categoricity. And it was some work related to the question: is it the same degree of categoricity and the strong degree of categoricity? And in the work of Nikolai Bajanov, me, and Marcy Malay, we solved this question. And in fact, we show that it is not the case when only one pairs of the structures can give this least property. And we asked it about maybe we can find some finitely many copies of the structures, such that all isomorphisms between that provide this least property. And then Turetsky recently solved this question. It shows that so the property of the least degree can be very tricky, in fact. So the structure A has the degree of categoricity 0 double, but for every finite number of computable copies of these structures, there are isomorphisms between corresponding copy and A, such as all they together are does not compute this degree of categoricity. So it is much more harder way to see why it is the degree of categoricity. When there is such, if for some n this is not true, when you say that the spectral dimension is finite. Here it is example, Turetsky provided an example, in fact, of the structure of infinite spectral dimension. So spectral dimension has some connection with the algorithmic dimension, of course. So this is my last slide about computable categoricity. Now I will say, speak about the functional categoricity, which is the notion of, it's a similar notion, but for some fixed subrecursive class of the structures. There are a lot of approaches studying computability of structures of models in the terms of some complexity classes, subrecursive classes. But here I and my co-authors developed some new, it was new when it was first published, approach in this area when we require that the domain is not just belongs to this subrecursive class. It must be very simple. So it is regular, automatic. So if this is you can see the primitive recursive class. So, my talk will mainly have a connection with primitive recursive presentations. But here we can think that the domain is equals to the set of natural numbers. But if we will study some polynomial time presentation and so on, but maybe it is more comfortable to consider a regular language instead of this just a set of naturals. For example, a set of binary strings and so on. So the domain, the purpose of this definition is that the structure, if it is infinite, you can always present, you can search this structure very fast. We have, from the beginning, we have an infinitely many elements. We do not need some time or some way, some infinite loop waiting for a new element in the structure. So we know we can take arbitrary number of different elements of the structures and we use them. So the domain is, for example, the set of natural numbers. But all other relations and operations must be primitive recursive or polynomial time or elementary or so on and so on. So the so I will say about the punctual, but I will in my talk I will say that it is the same as primitive in that sense. A primitive recursive, not primitive recursive here. It's just misprint. A punctual presentation is just any such copy, and the difference between this notion and the previous notion of computable categoricity and computable isomorphism, we need not the isomorphism, but its inverse must be a primitive recursive. We can easily can compute isomorphism and its inverse. The punctual structure is be computably categorical if A is punctually isomorphic to every its punctual presentations. And surprisingly, this notion was almost trivial. It is natural, but it's very hard to find some non-trivial examples of this punctual categoricity in contrast with the situation of computable categoricity. So the first natural example, it's empty structure, just not connected points. It's of course it's punctually categorical. Another example, we can take prime finite field and just consider it can be considered as additive group, and we just consider the infinite sum of this group, or we can consider as this structure as a vector space of infinite dimension. It's for me it is equivalent from the point of view of categoricity. So we can build isomorphisms very fast. If any two punctual presentations, we can reconstruct an isomorphism very easily, because we have in every copy we can take new elements and it's very far. You do not need to do some weight to find new independent element from the previous collection. So we can build the basis in these vector spaces very fast. But also the natural examples. But nowadays it's very easy to find that it's the natural numbers with +1 operations, and you can even add addition or multiplication and other operations. But still, this structure is not punctually categorical, and this holds for many others natural structures. The same. So these two examples was our first basic examples of the computable categories, but in fact they are not computably categorical. So in fact the arithmetic finitely generated set of the natural numbers, and then dense linear ordering is not punctually categorical. And this holds for many other structures, natural structures. It's quite difficult to find punctually some non-trivial example of punctual categorical structures. In fact, it's a result of Sasha Melnikov and me. There is a finitely generated punctually categorical structure. So the structure can be, it's not trivial, it's finitely generated. And it's possible, it's lately I've noted that it can be defined as a finitely generated semigroup. In fact, this structure, this semigroup, has the property that any possible punctual copy can, even if it is finitely generated, we can do not wait when some element generated will be generated on some fixed base. We can sufficiently fast to find some corresponding element in some standard code. And another example is more difficult. There is a punctually categorical structure which is not even computably categorical, so it is completely different story. So there are computably categorical structures which are not punctually categorical, and there are punctually categorical structures which are not computably categorical. And sufficiently recent result by me and Sasha Melnikov. And in fact, it's interesting dichotomy holds here. Every punctually categorical structure must be either finitely generated or locally finite. This is strange, but this it was very surprising to find such property, because usually you have no, in computable model theory we have no such strange division, because usually the structure can be not finitely generated as locally finite. It can be, and it does not make a sense. Here it has some sense in this property. So it is either generated from some finite set of elements, or if the first clause is not true, then every finite subset in this structure generate a finitely many substructure. So I forgot to mention in general in this array, when we study primitive recursive operation, it is not the same as primitive recursive relation. So this one of the difference between the classical computable model theory. We cannot replace operations by relations, because if a graph of the operation is primitive recursive, this does not mean that the operation itself is primitive recursive. And so here it is, so it's a locally finite. It exactly means that so the structure either has no operations, but or these operations generate some finite set if we start from another finite set. And if you say about, if we want to say something about the degrees of punctual categoricity, we need to choose some reducibility and consider the degrees relative to this categoricity. Here it is quite natural to consider primitive recursive reducibility. We are saying that F is PR reducible to G if F can be obtained from basic primitive recursive operations and G by composition and primitive recursion. So intuitively, that means we can again use G as external function, and in our programming language we cannot use infinite loops. But we can use some functions G as oracle, as just predefined function. If you can compute F using G in such way, then we say that F is G reducible, is PR reducible to G, and it's easy to show that it is. In fact, it's generates some degree structure. It is transitive and so on and so on. So we can, in fact, we can say about the PR degrees, it's a factor class under corresponding equivalence relation. And now it's absolute similar way to say that punctual structures can be as X punctually isomorphic for some primitive recursive degree X. If the the structures are X punctually isomorphic if we can using this degree we can primitively recursively compute P and P minus 1. And punctually categorical structure means that A is X punctually isomorphic to every its punctual presentation. So it's a similar notion. And the similar notion of the degree of punctual categoricity. And it was proved in 2017 by me, Sasha Melnikov, and Kengman and that every so a lot of PR degrees from the beginning are the degrees of punctual categoricity. If you take any function with a computable graph, then its PR degree, the function itself can be not primitive recursive, but this degree of this function is the degree of punctual categoricity of finitely generated structure. In fact, this is just some modification of our. It's a different papers published at 1 year. It's a theoretical computer science, and this is algebra and logic, the same year. And surprisingly, recently, we with Sasha found that this our old result can be, in fact, it gives the full description of all possible degrees of punctual categoricity for finitely generated structures. So it is only PR degrees of a function with computable graph. So it is the full description for the case of finitely generated structures. And again, if you study punctual categoricity relative to some degree, we again have this dichotomy. The structures will be either finitely generated or locally finite, which and it's natural to ask, do we have which PR degrees can be the degrees of punctual categoricity of locally finite structures? Because again, we have that any if a structure has some PR degree, it must be either finitely generated or locally. So this slide shows some connection between the notion of computable categoricity and degrees of punctual categoricity. We can define the categoricity spectrum, punctual categoricity, by the same way. It is a set of primitive recursive degrees such that A is X punctually categorical. And if you take, Nikolai Bajenov and me proved that these two classical computably categorical structures and all others classical structures which are computably categorical, but in fact have no degree of punctual categoricity. And for this structure, we can even describe the categoricity spectrum. It is all degrees which above all computable functions. So no, it's not one direction is trivial because the structures are computably categorical. Then if X is above all computable functions, of course it can compute all isomorphisms of the copies, but the inverse also holds. And my last slide, in fact, about punctual categoricity on a cone. I recall that for computable categoricity on a cone, we had a very nice theoretical model theoretic description of such categoricity. How the situation here is, again, we say that a countable structure is punctually categorical on a cone if there is some PR degree C, such that A is punctually isomorphic to every its copy, arbitrary copy, on a regular domain. So no, for primitive recursive, it's the same as the domain equals to the set of all natural numbers. So, and here we can use as oracle this C and the atomic diagram. No, it's not atomic diagram. It is it's functional atomic diagram. It's in fact it's a function. So we can glue all functions and operation in one join, and this B in fact can be considered as a function. It's not atomic diagram as a 0-1 valued function. It's many valued function. So it's this notion also some attempt to build to find some natural examples of punctually categorical structure, except which we had before. As I can remind, we have only few examples of the natural punctually categorical structures. And categoricity on a cone usually gives a full class of natural categoricity. But the theorem, it is a quite old result, which proved by me, Antonio Montalban and Sasha Melnikov, but it was published last year. In fact, there is a model theoretic description of punctual categoricity on a cone, but it's not so easy. In fact, I guess this theorem is waiting for some essential improvement. So in fact, here no computability notions in the right part. So it is purely model theoretic notions. But from the point of view model theory, it's quite difficult, quite unclear notion. It does not mean what it is. So one is quite standard. So in fact, up to some finite constant a some up to some finitely many constant, the structure is E-atomic. I will say it about below previously what is E-atomicity means. A is omega categorical. At these notions, it's quite technical, but essentially it means that every tuple B, for every tuple B, we can say from the beginning some finitely many some number, which is enough that any tuple, such that any tuple of C with n pairwisely different elements generates all representatives of all automorphism orbit in the structure AB. So for every tuple B, you can fix n, for example, n equals to 2. Then, if n equals to 2, then any two different, any pair of different elements must generate all elements, must enumerate some representatives of all automorphism types in AB. So it's quite technical, but in fact it's very at least it's model theoretic notions. It's but in general it is not so clear what the structural properties of such structures. That's all. Thank you for your attention.
Thank you for the speakers. Any question? Question? Okay, so looks like no question here. So let's thank you again, speakers, for all the speakers, also for the nice talks and for the giving us some new results, new ideas. Thank you again for all of you participants.
Thank you for your attention.
Yes, and Nicola, please.
So I would like to thank all the speakers for very interesting talks. Yes, and again, I would like to congratulate all of the participants with the World Logic Day. Yes, from the organizers. Yeah.
If you have any comments, you can speak if you want to say something.